This video aligns with the Ready, Set, Go assignment for the lesson Curbside and Clementine from Unit 5, Solving Quadratics and Other Equations. In the Ready section, you will be asked to find intersection points of two functions. You can use the support of graphing technology while working through these questions, but we will review how to graph them by hand. The first function in this example that is given to you is a quadratic function. It has been given to you in vertex form. Vertex form is helpful for graphing because we can see the translations from the parent function as well as the a value that tells us about a vertical stretch or compression. The second function is given to us as a linear function in point-slope form. Point-slope form is easy to graph by hand because we are given a starting point, x1, y1, and the slope, which is m. In the first function, we can see from the h and k values that the function has shifted to the right 2 and up 1. The a value is 1, so there is no vertical stretch or compression compared to the parent function. In the second function, we can see that the slope is 3, or 3 over 1, and the starting point is 1, 2. Let's take a look at the graphs of these functions. The parabola has been graphed from the parent function by shifting the vertex from the origin to the right 2 and up 1. Since the a value was 1 and there is no vertical stretch or compression, we will use the key points from the parent function to help build this curve. Those key points are over 1 up 1 and over 2 up 4 from the new vertex. To graph the linear function, we can start at a point of 1, 2, and then use our slope, which is 3 over 1, to build the rest of the shape of the line. You will notice that this graph intersects in two places. Those intersection points are the answer to this question. In the set, you will be asked to solve systems of equations algebraically. The two equations given to you in this example both start with y equals. Since those y's are equal to each other, the equations are equal to each other. We could set up an equation by substituting the linear function y equals 3x minus 1 into the y value of the top equation. In order to solve this equation, since it is a quadratic equation, it would be best to get our equation set equal to 0. By subtracting 3x and adding 1 on each side of the equation, our results will be 0 equals x squared minus 7x plus 6. We can then use methods for solving quadratic equations that we've learned in this unit. We could complete the square and solve, we could try factoring, or we could use the quadratic formula. This trinomial is factorable. The factors would be x minus 6 times x minus 1. Once we set each factor equal to 0, we will have the values for x. X equals 6 and x equals 1 are not the final solutions to this example, but they are the x coordinates of ordered pairs. We can then take x equals 6 and 1 and substitute them back into one of the original equations we were given. The linear equation does make the substitution process easier. When we evaluate for 6, we get y equals 17. When we evaluate for 1, we get y equals 2. These values are the the y coordinates of these ordered pairs, and these ordered pairs are our final solution. In the Go section, we will take a look at projectile motion. Remember that projectile motion is the height of an object over time. These examples will mostly be measured in meters for the height and seconds for the time. The negative 16t squared represents the effect of gravity on the object over time. The plus 20t represents the initial velocity of the object over time. And finally, the plus 10 represents the initial height of the object. Let's take a look at the graph of this function. What does the 0, 10 ordered pair mean in the context of this situation? Remember we discussed that the plus 10 is the initial height of the object. Therefore, at 0 seconds, the object is 10 meters high. Our x-axis is measured in time, and our y-axis is measured in height. Therefore, each ordered pair, or each key feature we'll be looking at on our function, has an ordered pair that is t, h of t, or time, height. The maximum height of this object would be 16.25 meters, and that maximum height occurs at 0.625 seconds. What does the 1.633 ordered pair, 0 mean in the context of this problem? If the object has a height of 0, then this must be the time that it took for the object to reach the ground. What about the key feature of an x-intercept on the left side of the graph? Since we can't go backwards and have negative time, this point does not make sense in the context of this problem and is not part of the practical domain of this function.